Hello, everyone, and welcome back to CSE 373. Today, we are going to continue yet another day of talking about really exciting graph applications. So today, we're going to be talking about this problem called minimum spanning trees. We'll talk about the problems that they try to solve, and we'll start talking about algorithms for how to find them. Today, we're going to focus on one algorithm that's going to end up resembling dijkstras quite a bit. And then next week, we're actually going to pick up with a different algorithm to solve this problem because it's actually a really interesting case study on a different type of data structure to help solve that other algorithm needs to solve the problem. But we'll talk about that next week. Today, we're going to talk about this minimum spanning trees and this thing called Prim's algorithm. So before we begin, I want to start with our learning objectives. And then in this video, I'm going to do a bit of recap of kind of what we've seen so far about graphs. So our learning objectives for today is to be able to identify what a minimum spanning tree is. We want you to be able to describe the cycle and cut properties of these minimum spanning trees and explain how Prim's algorithm utilizes the cut property for its correctness. And then we want you to be able to implement Prim's algorithm and explain how it differs from Dijkstra's algorithm. So first, let's start a bit of a review of what we saw last time. So last time we kind of, on Monday, it's kind of weird because we had that Wednesday holiday. On Monday, we kind of revisited Dijkstra's algorithm and gave you a little bit more specifics on how you actually go about implementing it. Particularly, we talked about in order to find that next closest node, we have that perimeter of nodes that are not yet known. We've visited their neighbors and we've proposed a distance. We always want to grab the closest node to the start vertex based off that distance too. And in order to have a data structure that efficiently manages a bunch of elements and gives each one a priority, maybe based off the distance, we wanted to use a priority queue. So Dijkstra's algorithm just uses a priority queue, and it's updating all of the nodes in the perimeter. Whenever it finds a new node, it adds it to the perimeter. If it finds a shorter path to a node in the perimeter, then it updates it, calling the change priority. And once we've kind of removed something from that parameter, we're marking it as known. And so then we know the shortest distance to that node. And we also talked about the runtime of this algorithm, but this kind of slide right here is going to be really, really helpful when it comes to implementing Dijkstra's on Project 4. So this is the place you want to have up. I want to remind you of that. Now, the other thing we talked about on Monday was this idea of a topological sort. So a topological sort is a sorting of some sorts on a directed graph where you're trying to respect the dependencies. So when we're going to interpret the graph as saying when there's an edge between u and v, means u must come before v. So we're saying here that all of these dependencies must be respected in a topological ordering. And so we try to describe some algorithms, some approaches to that. What we ultimately settled on was we needed this idea of a reduction, where we tried to reduce the problem of topological sort to a problem we already know how to do. So reductions are general problem-solving techniques where you take a problem you're trying to solve and change the input so that it can work as another problem you already have an algorithm to know how to solve. And then that algorithm will spit out some output, and then you transform that output somehow back to kind of your original problem. And so reductions are something that we've been using kind of our whole time as programmers, like in our programming career. But this is giving a word to it, of solving one problem with an algorithm you already know for a different problem. And so we introduced for topological sort this idea of the reduction, where we want to reduce to BFS. And importantly, in a reduction, you change the input and output. You don't change the algorithm. We talked about a couple iterations of trying to use BFS that failed. And then our idea was, well, if we change the graph to have this secret ghosty node at the front, and then run BFS on that, then we get the right kind of output. But we have to modify that output to remove the ghosty node. And I said at that point, we have achieved sweet, sweet victory. However, I was mistaken. We did not achieve sweet, sweet victory. I gave you a wrong algorithm. So what went wrong? Why did I tell you the wrong thing? So BFS is not going to work for topological sort. Remember that BFS always explores things level by level. So it always finds the shortest distance in terms of the number of edges. So it's possible that in this breadth first search, you might start at A and then visit D, but that's not going to respect maybe a long dependency chain to D, like A to B to C to D. So breadth first search is actually kind of scuffed here. It's not going to really work. Now, why did I end up spending a big part of lecture on Monday talking about breadth first search for this algorithm that doesn't work at all? Well, it's because I made a mistake, and previous instructors also made a mistake. People that write algorithms make mistakes too. How this came about in making its way into the 373 slides is it started off as kind of a thought experiment in the notes from a previous offering. And then it got adopted by a previous instructor, and then I adopted that previous instructor slides like, oh yeah, this algorithm sounds so clever and cool. And it fits nicely in this idea of reduction. So let's talk about that. And it just doesn't work. It was actually funny. I was messaging one of the previous instructors. I was like, wow, this is so cool. I've never seen someone try to solve this problem before like this. And I can't find anywhere on the internet that does either. But that's so cool that we were able to come up with this. And then in hindsight, probably we couldn't find any other sources of this because it didn't end up working. So I'm sorry for that confusion. That whole idea of reducing Topo Sort to BFS just doesn't work. And this is actually why one of the things we're not able to do in 373, which is really important for algorithm design, is being able to prove why your algorithm works and being able to make statements as what properties will be true in order to make them work. And if you're interested in talking about how we describe algorithms more formally and talk about ideas for proving that something works, that's kind of where a next follow-on course to 373, 417, that talks about algorithms will do. And we'll actually start giving a bit of a flavor of what it means to kind of describe why an algorithm works in today's lecture when we talk about these minimum spanning trees. Now, I want to quickly show you, because since I already introduced the idea of Topo Sort, and that idea of what a Topo Sort is and kind of what properties we need for it to happen are important, understanding our wrong algorithm is not important because it's wrong. What I do want to quickly show you are the correct algorithms to do topological sort, but they're slightly more complicated, and I don't want you to worry about them too much. So I'm not going to test you on being able to implement these other algorithms that I'm going to show you in a second from scratch. But I do want you to understand kind of a topological sort, what a topological sort is, in theory, how to find one, but the specific algorithms I'm going to show you next are not, the details of them are not important. There are two main algorithms for doing topological sort. The first one is called Kahn's algorithm, which is in some sense like a modified breadth first search. And whenever you hear modified, you know it's not going to be a reduction. Doing reductions is or modifying the algorithm. Reduction is all about just modifying inputs, outputs, and using a pre-existing algorithm. So Kahn's algorithm kind of works, and this kind of, the intuition is you always peel off nodes that have in degree 0, because those are nodes that have no prerequisite. And you can show that any DAG that's not empty must have a node with in degree 0, otherwise it would have a cycle. And so that's the ones with in degree 0 will always be the first ones in the topological sort. And then you kind of peel that node off, kind of remove it and all of its edges, and then go find all of the next nodes with in degree 0. So Kahn's algorithm is kind of like a modified BFS, where you kind of explore all nodes with in degree 0 and kind of remove them from the graph, so you can create new nodes that don't have any dependencies once you've listed out that new one. So that's kind of one very popular one. There's also this kind of cleverly simple but also very complex algorithm that involves modifying DFS. The idea is you run DFS, start at a node, run all the way down its path, and then you add the nodes you visit to a list of visited nodes, but in reverse order. So you always do a post-order traversal, meaning you add yourself after exploring all your children, and then you add yourself to the front of the list. And kind of somehow this kind of magically builds up a valid topological ordering, with the slight addendum that you might have to run DFS multiple times to make sure you visit every node once, like if you started like kind of later down in a chain. But by kind of doing this post-order traversal, only adding nodes that you haven't visited yet, and always adding to the front of this list, this kind of cleverly builds up a topological ordering. Understanding why these algorithms work not important for our class. I just wanted to mention, in case maybe you're doing an interview or something and they do talk about topological sort, you kind of know some algorithms now to actually go about that. So what I want us to talk about for the rest of the videos today is this minimum spanning tree problem, but I'm going to pick up with that in the next video.